doesn't matter. Okay, welcome to now the lecture number 6 in computer algebra in the summer term 2025. So you see there are not, because we always have lectures that, exercises that we do not record, there are actually not so many lectures. There is a maximum of one left, maybe not. Yeah, we'll see. Actually, there are so many more topics that we could discuss here, but it's also kind of a busy time for me, so I'm not completely sure. Okay, so today no exercise, but then exercise next week, a little bit a combination about the two things that we covered in the last lecture. In the lecture this time, the last lecture was about Runge-Kutta method, and today we go a bit in the direction of Richardson extrapolation, but this again, as was lecture 4, is kind of a case study of a relatively simple side project that we did. So actually, real research that we discuss here. Yeah, and for this we also have this this link down here. So there's a paper. So this is based on a paper that we've written about a small side project. So it's not a very complicated project, and it's not a very complicated scientific work. But I found it pretty interesting. So it's about implicit shells. So okay. So implicit shells. Why do we need implicit shells? So in engineering, we often have to somehow represent objects mathematically, yeah. And one way this is usually done is by using triangulation, yeah, of something. So you represent objects by a triangulation of their surface. Okay, so this is maybe the most common way of doing it. Then there are more complicated spline representations and so on. These things are common. They have, they are completely freestyle. They have the disadvantage, in particular, if it's triangles, that they have that if you require a derivative of, say, the normal or so on, they will be discontinuous, yeah, and they will actually be not very accurate, yeah. So unless you're using splines, then they become they become more accurate again. But all these objects are somehow what is it? Of finite support, yeah. So they will not cover the entire object, but you discretize it, so you cut out pieces, and then you have a spline. You have either a triangle or a spline in between that, and then you always have these places where you glue them together. And in this place, they are usually not continuous, yeah. Usually they are continuous, but they don't have infinitely many continuous derivatives usually, yeah. And usually not even the first. I mean, if you have triangles, then not even the first derivative would be continuous in this location, which may or may not be a problem. And in particular, and I mean, this is an important point. Many objects that we are dealing with actually have corners, so they have discontinuous derivatives, and they are then well represented by a triangulation. I mean, if it's a box, yeah. So, however, this also contains a lot of information, and there may be some objects that can be represented in a different way more accurately. And actually we did have these problems in what we're mainly doing, fluid dynamics. So for example, we wanted to simulate a sphere, yeah? So now how are you doing this? A sphere, I mean, so of course, now you can discretize a sphere with triangles, yeah? So now if you want to simulate this at a very high Reynolds number, and you have a very thin boundary layer, what you observe is that now think you have discretized the sphere with triangles, then actually the sphere has corners, which you may not see if you look at, you know, optical representation of your mesh, yeah, because it's many triangles, but still they have corners, and the boundary detachment will start at these corners, even though they are very, very, you know, they are not, so they don't optically look like corners, but for an accurate simulation they are corners, and then they completely modify the behavior of your flow. So you get early detachment of a boundary layer if you have a sphere represented by triangles, in comparison to when you represent the sphere by its implicit function. So because I mean, for a sphere this is pretty simple, yeah. So you know how this is can be done. So a sphere is represented if you take its coordinates squared, and okay, so this may be not. I mean, this is. I should write this in a different way. I mean, this obviously works, but it gives the wrong offset. What is this? Okay, I should write it like this. Right. So the sum of the squares of its different coordinates. Yeah, of course, now this is centered in the center of the coordinate system minus the radius squared, where this is 0. You have the sphere, yeah. So and now it is possible. So this is what we call an implicit surface. Yeah, there is a function for which we can define a contour, and usually this contour, I mean, can have any offset, so we can, without loss of generality, say there's a function that has the 0 contour, yeah. So the 0 contour represents the object. And this can not only be done for this simple sphere, but also for more complicated objects, even though the implicit function can become very, very complicated, because it is a global representation of the object. Yeah? So the function everywhere includes the information on everything here. Yeah? Yeah, so now you see a sphere. So this representation is much more efficient for a sphere than a triangulation. Yeah, because you need many triangles to get an accurate representation of a sphere. So alone reading this from a file can kill your software. However, if you want to represent a car in this way, this can get pretty challenging, and maybe it's less efficient. So anyway, implicit surfaces is an interesting. I mean, you can also, by the way, you can also kind of do this, piecewise in a sense, yeah. So having a piecewise representation, then you also can have corners in this context. So now this gives you now representation of an object, and this let me see, I'm not completely sure whether I have this on the next slide. Yes, now we come to the shells. So what you have is not a representation of the object, but you have a representation of the surface, right? So this may be sufficient if you have a closed surface like a sphere, and you say there's one part is inside and another part is outside. But suppose, and this is often the case, you actually want to represent an object that is made up of the surface, like a wall. Yeah? So then suddenly you have a thin object. Now suddenly you have the problem that mathematically your minimal surface, is a mathematical surface. So its thickness is 0. And in reality, if you want to build something like a wall, yeah, or you want to 3D print something, this was also the application here. You want to 3D print an object, and then this surface actually has to have a thickness. Yeah, so it comes from a surface to a shell. Yeah, so it's supposed to have a thickness. Now by the way, there are structures that can be pretty well represented by these implicit functions. For example, there's something called triple. Oh my God. Periodic PTMS. Periodic triple minimal surfaces. Okay, I don't know what. Okay, so there is repeating structures, yeah, that are useful for building structures like filters and so on. Like what is this called in the car that filters out the NOx, give me the word. You don't know. So what is the thing that cleans the air that comes out of the exhaust of a car? It's called I'm just missing the word. I'm making, you see, this will get a lot of clicks on YouTube. Yeah, this is the, but you don't know either.
The word, like in English.
It's the, oh my God. Well, something that makes things react. I don't know why I'm missing the word. So, okay. Fun for the world. They have it on YouTube. Yeah? Anyway, so there are lots of use of these things, but if you want to build them, they actually have a thickness. Okay? And in particular, if you want to print them, they need to have a thickness. Nowadays, because we're doing things by 3D printing a lot. So then you need to take your minimal surface and put it into a shell. And now the question is, how would you do this? So the first idea, and actually this is, I've seen this on conferences and discussed with people, this is the way it is done in practice. Yeah? So you take the surface again and you move it a little bit in one direction and you move it a little bit in the other direction. Like what you see here. So suppose our surface is given by the sine wave. Yeah? So what then you do, and okay, turn off your brain, don't think hard and say, okay, we just move this up and move this down, and many people then believe they have created an excellent surface of constant thickness, yeah, because this is what you usually want to have. You want to have either, say, maybe not a constant thickness, but a controllable thickness, right? So, and if you actually do that, what you observe, if you look here carefully, is that in this place here, this shell is pretty thick. I mean, you know, that's actually stupid, yeah, because the bending makes it more, you know, harder, like accepting more pressure, right? Yeah, already. But in addition to this, you also make it thicker here, okay? So this thing would not break in this position, obviously, yeah? But there, in the position where it's actually weak, you make it thin. So if you wanted to control it, you would rather make it thick here and thin there. Yeah? So what's the problem? The problem is if you naively just move this up and move it down, you do not get a surface with finite thickness, because you see, because you're always okay. The way you're moving it is not normal to the surface. Yeah, so you're moving because you're moving always 0.3 up, right? So you're moving 0.3 up. So here in this position where you are on top of this line, you really get the 0.3, but you also get the 0.3 here. So this distance from here to here is 0.3. So now you could easily see that if you look normal to the surface, because, I mean, this is an arbitrary coordinate system, right? So you should rather look normal to the surface, and there it's much thinner. Yeah? So now is a problem. So this is the problem statement. If you want to extrude this surface so that the surface becomes a shell, it's not sufficient to just scale the outer one up, yeah, somehow. Then you will get an object of different thickness. Okay, and now we want we try to see how we can actually do this in a better way. And this here is done by what we call an offset function. Now, the problem, as we just discussed, is that if we move or scale the functions around in order to build this shell, we are not moving them in the direction normal to the surface. Yeah? So what we need to do is we need to move it normal to the surface. Yeah? So, see, we are now assuming we have an algebraic function, and say this algebraic function is this f of x is equal to 0. Now, what we like to get is another function phi, phi that is equal to 0 at a given distance h. Yeah? So the distance h is supposed to be later it will be half the thickness of the object, because we do this in one direction and the other direction here, obviously. Yeah. So we want to define a new function that has its zero contour at a given distance h. Yeah. And by the way, so this implicit surface, so assuming this is a continuous function, this f, yeah, so there will always be, so it's, the surface is where this function is 0, yeah. So there's an area inside and there's an area outside, right? So indicated by f being negative or f being positive. So therefore there's also positive, so an outside shell and an inside shell, and this will be indicated by h and minus h. Yeah? So if we want to go in the direction of the normal with this, what we have to do is, of course, to get the normal. And then what we are using is our favorite function, namely the Taylor, the Taylor expansion. Yeah. So we see what we're doing. So when defining this function here, we take the first order Taylor expansion, which we say we have the f, and then we take the derivative in the direction of the normal, right? So this is a directional derivative, right? So we have to so in order to get the directional derivative, we need the gradient and the direction, right? So we have to multiply the normal with the gradient in order to go in the direction of the normal, and then we go a distance h. Yeah. So this gives us exactly So we go a distance h. Yeah, because we want to move to a distant h. So this would be the lowest order approximation that we can produce according to the Taylor expansion for a function that has its zero contour in a distance h. Right? So it's not accurate, yeah? But it is the lowest order approximation thereof. For this, what we need to have is, of course, the normal. And the normal also comes out of the gradients. Yeah? So you can compute, so the normal is, okay, maybe this is not, okay, I don't know whether this is intrinsically clear. It is. Okay, good. So, I mean, you have this, I mean, you could say that it needs to be orthogonal, so the gradient is orthogonal to the surface because inside, on the surface, h is the gradient, there is no, so the function, no, on the surface the function does not change, right? So then the gradient tangential to the surface is 0. Yeah, so, right, so the part that is normal is the part that is actually non-zero. So you calculate the gradient, and then in order to get the normal, of course, you have to normalize this by dividing by the magnitude of the gradient. So, now this should get a little bit simplified, yeah, because this is now, you see, this is how the function looks like. So we have the original function, and we have the gradient of this function times the gradient of this function divided by the magnitude of the gradient of the function times minus h. This is not very much simplified. I try to use assumptions, so we had this in the exercise a lot, yeah, using assumptions to say, okay, this is 0 because I was in the expectation that it would not be able to see that this can be simplified because, I mean, it may not be able to simplify it because the gradient can be 0. Actually, there's a problem, right? Yeah, I mean, this whole thing doesn't work when the gradient is 0. So Mathematica here did not simplify it, so you know, I just write it by hand. Okay, I got two versions of the same thing, yeah. So I can define, you know, you can use function overloading, yeah. F of x or just f and x as an additional parameter, yeah. So it doesn't matter. So the one f of x is using f of x here, and yeah. Okay, so you easily see that this is the simplification of this. So yeah. So the lowest order approximation that we can produce for an offset function that has its 0 contour at a given distance from the original surface is the original function minus h times the magnitude of the gradient, right? Good. So this is how we get there. So, I mean, there is one important message that I try to convey in my numerics classes, is always you need to solve, I mean, you want to solve a problem, so don't think about how you solve your problem best in the beginning, right? So, because, yeah, so what you always need is to find a way that solves your problem even as stupidly as possible, yeah? Because once you need to get a handle, and this is what we later see here, yeah? So you need to get a grip on a solution, and if you have this, then there are mathematical tools that help you to improve that, yeah? So there's always important just to get started. Like you do Euler forward, and then by using Euler forward and combining these things, you come to higher order Runge-Kutta methods. But you know, you cannot talk about this unless you start with Euler forward. Yeah? So all the Runge-Kutta methods have this Euler forward somehow built into there several times. Yeah? So, and now this is pretty much the same. Actually, you can reformulate this and see that this is Euler forward integration. Yeah, if you, okay. Now we have this primitive function. Using the first order offset function, yeah, so what we can now do is we define a function, for example, this sine function. So how would we do this? We take sine x minus y, yeah, so, okay, so how do we define function? So we have y is equal to sine x, yeah? So, and now we are looking for a 0 contour, so we put the y on the other side, so this would be 0, right? So, then this gives us than the sine function. And now, as we have defined this offset function, what we do is we take our function f of sine x and y. So if you want to have a different position here, and we have the coordinates. Okay, what is this? Yes. So actually, okay. I mean, in order to plot it, it's now an implicit line in a plane, right? So later, of course, I mean, we want to have x, y, z. So I have a surface in three-dimensional space, and now we have a line in two-dimensional space. So this is now the coordinates x and y, right? And here we put our offsets, to a given number, 0.5, and then, of course, we get out these things here, sine x and what we have here, right? Okay, so now, of course, we can plot this. Yes, okay, we do a contour plot of this now. And this is what we get. So the blue line here is the sine wave. Yeah? And I believe it is, I would say it's believable that this here is a better representation of a shell than we had before. And if we do not believe it, we actually, I don't know why it's plotting it like this. We have here a comparison. Now, this is not a good thing for colorblind people like me. I guess, okay, so this thing here was the offset, IRMB. Okay, we can see it, right? Here with the tooltip, yeah? 0. So this is just the offset, yeah? And you see, as I said before, the thing gets thinned out in this area, while here, I mean, here it's obvious that it has to match, because the normal here is just the y direction, yeah, and we moved everything in y direction. So here on top, yeah, where the derivative is 0, yeah, so we just get this offset, yeah, and the same thing here. So I think this was already kind of successful. Yeah, this very simple method is not too bad actually, right? But what about, okay, no, something else. I just mentioned that this is similar to an Euler forward integration in the sense that we just take we just take the first order Taylor expansion, yeah, and go by a step h. Now you could think about this in the following way. You had an implicit function for a surface, and now you generated a new implicit function for a surface with a given offset, which is again an implicit function. So you could, of course, take this implicit function and make an offset to it, right, in order to get another surface that is further out, yeah? So, and this could make you think, how should I do this? Should I go in one step? Or should I potentially, to the surface that I want to have, or what I could also do is I decide to go a smaller step and then take another step until I reach where I want to be, right? And these two things will not be the same. In particular, because we have low order approximation. Yeah? So because the normal of our function f will change in space. Yeah? So let's think about it this way. Now we have, now we could do two steps. Yeah? So we simply apply our function phi, yeah, which I indicate with 1 means this is the first order. Yeah? So we apply the function phi to the function phi of this onto this function. Yeah? And now, so we apply this twice. So we go only half the distance because we want to end up having the same shell. Yeah? So this is, we do this h half and h half. So we split up the same way that we want to have in two steps. Going forwards here and going backward there. And now, okay, we put in here the numbers, and yes. So what this here is the algebraic solution of this. So what we observe here is, we had the original function, then we have kind of the first step, and then we have this here comes from up to here. This was what we had before. And then we have this here on top of it, which looks a little bit ugly, yeah, but not so much, yeah. So now again we can plot all of them together. Now it becomes horrible for colorblind people. Now even colorblind people, when they count the number of these plots, they see that there seem to be less lines there. You can count this up, obviously, 1, 2, 3, 4, 5, and there would be 1, 2, 3, 4, 5, 6, 7. So now you could say there are 2 missing. I would say there are 2 just on top of each other, meaning, that's a good sign for our function because it appears that going the full step and going twice the half step gives us pretty much the same result, right? Okay, nice. But potentially this is just because we have a nice sine function. This is cheating in comparison to what we could have, and the other thing is our shell was not too big. So now what we are going to do is we do the same thing again. We use a larger h. Previously it was 0.5. Yeah, now get a larger step. So if we do a larger step, we start to see some difference. Now we have to figure this out. I think there's a tooltip. Maybe this is helping us. Yeah. So right. So this here is obviously the one-step version. Yeah. So what we observe is there is some bulking out. We can also, we have Mathematica. Why don't I do it even more ugly? Yeah. So 2.5. Yeah. So it surprises me. Okay, but anyway, yes. So we have here some bulking out of the one-step function, and we have much less bulking out of. We have bulking out, yeah, but much less in the two-step function. Yeah. Actually, you see, there is of course a problem. So how do you define an object with constant thickness? Yeah. If this is getting too large, yeah, like, okay, I'm kind of running out of space here. Where did I? H. Maybe I have to. get this. Right, I mean, so, you know, if you want to have, if you want this thing to have constant thickness, yeah, this is not a well-defined, this is becoming a more and more badly defined problem, yeah, and there is, and so you actually get into trouble, actually for very large, okay, so now this is, you see, this is actually interesting. If you go further out, the one with the 2 steps even kinds of gets further away of this. Yeah, I mean yeah. Let me go back to it. This is I'm overdoing it here. Yeah, what do you want to say?
The funny thing is that in the end, the recursive relation has 1 minus this thing, and if that is bigger than 1, that's why that happens. So the step has to be less than 1 for it to be, because there's a change in the step.
No. The step does not need to be less than 1. I mean, this is. We are not. Okay. Now I confused you with the homework that I gave you, because we are not talking about the next order. We are talking about taking 2 steps.
Mm-hmm.
Yeah? 2 steps, not next order. Yeah, we need to be, okay, we need to be careful, because so you may know when you had a method of higher order and you do bigger steps, then you get the Runge phenomenon and then you get more oscillations. But this is not what we observe currently.
But what you're doing is you have one function, you get 1 step, and then you get another step
with the other function. Yes. Yeah, I mean, it's okay. Now we could put a lot of interpretation into this. I mean, we see there are different solutions, and we see that at least for this case, I would say from the picture norm, the 2-step thing seems to be more trustworthy, right? So that would be better. So now what do you want to say?
Just for curiosity, could you use 0.9 in just
okay. 0.9. Just for curiosity. So, what do you want to see?
So if it's bigger than 1, for example, 1.1, you would see again this behavior.
So you mean because the function oscillates between 1 and 1?
If h is bigger than 1, you see this behavior, and if it's less than 1, okay, no. Or
okay, how much do we need to zoom in?
okay,
Yes, there is some overshoot, right? So you say that there is 0 overshoot for 1.
that should be problematic. Okay, no, just
I'm not completely sure that there is no overshoot for 1, but it is possible that there is no overshoot for 1. But I think this is very much problem specific. Yeah? So you're a little bit in danger to thinking too intuitive to the things. Yeah? Don't believe too much. Yeah? It's okay. I return this to its original value. So then I have it for next year. Now we come to the Richardson extrapolation. Okay, Richardson extrapolation is a very important thing. Now usually I teach it more to civil engineers, and for civil engineers I always have to say Richardson was a civil engineer. Yeah, so this is, mathematicians don't usually think that practical. So Richardson did something extremely practical, but also he did something that other people before him have already invented, and somehow it's tied to his name. So this was already used by the Japanese to calculate pi to high precision by hand, yeah, a few centuries earlier. But anyway, so I actually recommend to watch one of my videos on Richardson extrapolation, because I think not everything, I mean, it's pretty simple, but not everything about this is cleared, is totally clear to everybody. But okay, so what actually is this? And it's very powerful, and when you need it, it doesn't work. Richardson extrapolation is the observation or the idea that if you have acquired numerical solutions on problems using different step sizes, so what you usually need is a smallness parameter. Yeah? So there is a variant which is basically the same, that is called the Aitken extrapolation. That kind of requires no smallness parameter directly, as long as your process generates a series of solutions, not a series, a sequence of solutions. Yeah. So then you can use Aitken extrapolation, which is mathematically the same, but is a different name from a different guy. So the idea here is you use one numerical method. It needs to be the same numerical method, and it has to be defined through one smallness parameter. Yeah, that's very annoying to people trying to solve partial differential equations where you have grid spacing and time step. So you have two smallness parameters. You have to have one, okay? So you have one smallness parameter. You have to have one smallness parameter. And then the idea, and I've mentioned this in previous lectures, so this is one of my most favorite equation here is that a numerical approximation is given as a series of the solution that you're looking for and error terms. Yeah, so you can expand hopefully, yeah, I mean, this is when Richardson extrapolation works, that you can expand your numerical solution in terms of the real solution and the hierarchy of error terms that come with the smallness parameter. Yeah, so this can actually so this is under the assumption that you can make a kind of a Taylor expansion, yeah, of your solution for a small smallness parameter. So this usually here looks like this. So you have the real thing plus an error sum over error terms, which, this is important, do not depend on the smallness parameter, yeah, times the smallness parameter by a power of I. Yeah, so this is the series expansion that we here assume. So if your numerical method works like this, and usually they do, so there are some that don't. For example, Monte Carlo integration does not work like this. Yeah, but usually finite elements Runge-Kutta, control volume, you name all these things, yeah? So deterministic methods work like this, as long as you can define one smallness parameter, yeah? Meaning, you have to stick to a specific kind of mesh. So if you refine one part of your mesh by a factor 2, you also have to refine everything else by a factor 2. Yeah? No stretching something, they need to be the same method, the same kind of mesh. Okay? So if this is the case, then you can expand the error like this. And the idea of Richardson now was so you, since this looks like this, what you can do is you combine two solutions with different smallness parameter. Yeah, like in our case, yeah, we want to go a given distance h, but we can go there with a different number of steps. Yeah, and if we go there with a lower, so the difference here is if we go with 2 steps the same distance, we have our smallness parameter is then 1/2 of what we have when we go 1 step. Yeah, and if we go this in 4 steps, again the smallness parameter is being smaller. So the idea is we combine the solutions in order to eliminate some of the leading order error. So usually the first term here. Yeah. So now think about like this. So we want that there is a combination of the solution 1 going in 1 step and the solution going in 2 steps. How do I indicate this order max? Yeah, here. So n, yeah, n is the number of steps. Yeah, so and here we divide h by n, right? Yeah, so this is now indicating 1 step, 2 step. Okay, so this now is supposed to be our solution, and the higher order steps. Yeah, so if I weight this, they would come with, here they would come with 8. So the first error would come with h 1/2 and h divided by 1 and h divided by 2, and this we like to be 0 because it's the first error that we have. Yeah. So and then we solve this for the weights, and then we get these weights. Okay. So, and then this implies if we do this by 1 step and if we do it by 2 steps, so what we have to do is we have to multiply the thing that we solved 2 steps by 2 and the one that used 1 step by -1. Yeah? So now we go 1 step and we go 2 steps and okay, get these functions out. So let me see. So we get right. So this is 2 steps. Yeah, it's an okay. We define this as a recursive function, right? Yeah. So here we can test this out. So when you go 2 steps, so it puts the function into itself and more and more and more, right? And also we see that this is true as we are supposed to test our functions. So now we have computed our weights. We do it here 1 step and 2 steps, and now we solve the same problem here again. Yeah. And now it becomes even more complicated for me. So I plot here only, okay, I plot only the two-step version here, and on top of this I'm plotting the Richardson extrapolated version here. So, which, okay, gets a little less overshoot. Actually, by looking at this, I have to admit that it's not easy to see whether this is an improvement or not, right? It's not easily optical offsets. So this, what is the one with
If I am right, the last one is the one that looks like this, the one above. Yes, that one.
okay, so usually, okay, so this is offset to be T, okay. So now we can argue. Now you can argue whether this is whether this has given you actually an improvement. So the thing. Okay, we need to be careful with what we call an improvement, because now this function has supposedly a better convergence. Yeah? We have not tested it, but it has a better convergence. So having a better convergence does not necessarily means that for any value that we put into it, we get a better result. Yeah? It's a very important practical message. So we professors, I mean, if you think about fluid dynamics, so you'll hear a lot of professors that say the only thing that you should do is using spectral methods, right? Because they have the highest order of convergence. So, thus having the highest order of convergence always means you get the best result. So what does it mean? It means that there is a point in resolution where this method will beat all other methods. Yeah? However, for a given solution, for a given resolution that is not infinitely fine, like here, for a given h, which is not very, very small, the lower order solution may actually be better. It may actually also be better behaved. That's very often the case. So I think I talk about this or at least I hope I talk about this in this talk that I have mentioned. So the problem, always what you have to remember when you use the Richardson extrapolation, so it improves the convergence. So if your step size is sufficiently small, it will certainly give you a better result. However, if you look actually what it does to the remainder to the remaining terms in the Taylor in this expansion, yeah, that you have not eliminated, they get exponentially larger every time you subtract one term below. So you're moving error from the low order terms to the high order terms, what you want to do, because you can reduce the high order terms by reducing the smallness parameter, right? So, but then you have to do this. You have to reduce the smallness parameter because otherwise, they pile up error there. And this is also what we call the Runge phenomenon. So Runge, the guy from the Runge-Kutta method. So he observed, mathematician, yeah? So what he observed was, I mean, he thinks like a mathematician, I do higher order, I get a better result, right? So, and then he did this and observed that he did not get better results. And actually, the reason for this is what I just described, that if you use Richardson extrapolations or some other things that Runge did, so higher order methods, you are piling up error on the higher order terms. Yeah? So on the prefactors are the things that I okay, see this prefactor here. Yeah? So by eliminating the zero order here, you get more, you make this thing for the next order larger. And actually you observe exponentially. So this will go up with I exponentially, right? So meaning that if you don't change your resolution, then finally if you make your order larger, your error gets larger in practice. Yeah? So, meaning, yes, you should use higher order methods, but only if you also reduce the crit size. Yeah? So using, I mean, because what people from a practical point of view think they could do is to use higher order methods in order to use smaller crit size, larger, I mean, coarser resolution, right? But this is not true, unfortunately. That's not a trait that you can do. Yeah? So higher order methods are only good with smallness parameters, yeah? Which is a bit of unfortunate. And now you have to say in practice. In practice, actually everybody uses control volume and they are intrinsically second order. That's the reality. Even though we know for 60 years how to build spectral methods. Yeah? Because they are still better in practice. Okay. So, word of warning, yeah? Right, so I'll check this. I mean, I'm an absolute fan of Richardson extrapolation, but you have to know, I mean, I'm also completely frustrated by it because when it would be most useful, it usually doesn't work. Okay. Kind of. So, now what we can do, so Richardson extrapolation usually only eliminates the first order term, and then now there are different ways how you could proceed. So you could apply the Richardson extrapolation recursively, yeah, to get to higher and higher and higher order. Here we want to do it in a little bit a different way. Now you can argue whether this is a better or not. I don't know. Probably I should investigate, but let's just have a different approach, right? So instead of applying the Richardson extrapolation recursively, what we can also do is we can compare not two solutions, but more solutions of the low order.
You mean you make the first step?
No, yes, I'm taking the low order method.
Okay.
Yeah, the lowest order method that I have. And now because I compared one step and two steps, right? And now I can also compare this, for example, to three steps. Yeah? So, and then what I want to have is, we're taking another step, I can eliminate another term from this. So, and this is what I would do here. So I'll say that the combination of all of them should give me the function itself. And then I say that, that actually the one that we had before was this. So I want to eliminate the first order error. And then I also want to eliminate the second order error. Yeah? So they are put to 0, and then I get these numbers here. And now, of course, this can now go on indefinitely. So we can basically specify what we would like to do. So what we see is that this error, that this function that we get out of this is always has the function that we want, so the f itself. Yeah. So this is what we want. So so all the weights have to sum to 1, that we actually get the function out. Yeah. And then for the different error terms that we want to have, we always have the weight times h divided by I, so how many steps we do, by the power of I. Yeah? And this for as many terms that we want to use. Okay? So then this means that, now this is completely general. This doesn't have anything to do with this particular function. The only thing that we assuming here is that we are talking about the function that is first order accurate only. Yeah. So because if you start with a function that is already second order accurate, you don't need to eliminate the first order term. Yeah, so you will end up, you see, then you would keep this here away, and instead, but you will still have this, and instead here would go to the third power. Yeah, right. So, and then also, by the way, if you have, then you would also think, do I have a symmetric method or an unsymmetric method? Because in a symmetric method, you would only eliminate, right, every second one. Right. Okay. But now, since we have the lowest possible order, we have to eliminate all of them. Yeah? And if we have, so this is what I said in the beginning, do something stupid. Use the lowest order method that you can have, and if you have them, then we have methods like this one in order to get this to any order that you want to have. Yeah? So here, so we get, for example, going to third order, we get these weights going to, let me see, so this is, so this is third order, then this would here be fourth order, and this would be fifth order. Yeah? So these parameters are general, so all you need to do now is to, is to evaluate these functions several times and get multiply this by these factors, and then you get a more accurate solution. By the way, what's the time? Yeah, we are kind of close to the last slide. So why don't we always do it like this? For example, in Runge-Kutta. So why is Runge-Kutta not usually built up in the Richardson extrapolation?
It's something similar, right?
Yeah, but it's similar, but it's not the same. Oh, okay. I have a better question. So suppose you want to integrate, you do an integration, right? Just usual function integration, yeah? So then there are several methods. So there's Trapez method and Simpson's rule, and then there's Gauss integration. So now Simpson is better than trapezoidal integration, right?
In theory, probably yes. Well, I don't remember the errors, but yes.
I mean, it's higher order. It's converged. Okay, it converges faster.
Okay.
So it eliminates one term more. Now it's easy.
Yes.
It's easy to derive that if you take the trapezoidal integration and you do a Richardson extrapolation on the method, not on the result, then what you end up is the Simpson's rule. So the Simpson's rule arises from doing a Richardson extrapolation to the lower order method. Yeah, because all the Simpson rule does is eliminating the first order term by keeping the same spatial distribution of your sampling points. Now is the Simpson rule, or if you now you could also apply Richardson extrapolation again and again and again. But then there is Gauss integration, and this Gauss integration uses the same number of points. Okay, it's not really true in practice, but so from partly philosophical point of view, you see the same number of points as a simple trapezoidal integration. Yeah. So to get the same accuracy as, or if you get higher order, yeah. So, and the similar things apply to Runge-Kutta time integrator. The thing is, Richardson extrapolation gives you a method of higher order from a general procedure of, making the step smaller and smaller and smaller. But this is by no means the most efficient way to eliminate higher order terms. And this is nowhere more visible than with Gauss integration. Yeah. So because if you use Gauss integration, so what is Gauss integration? So Gauss integration basically means you pre-compute the positions at which you should evaluate your function to get an accurate integral. Yeah, and what you observe is that all of these are non-rational numbers. Yeah, like square roots. Yes. So they real numbers, not rational numbers. Yeah. And this never comes out of a Richardson extrapolation. Yeah. So Richardson extrapolation, you have your fixed grid size, or you have your you always need to increase your step by this, like in an integer format, yeah. So you have to double, maybe you can triple, yeah. But you have you cannot decide where to put your evaluation points, yeah. So what you do with Richardson extrapolation, you add one more entire simulation, yeah, at yet another higher resolution, in order just to remove the next order error. Yeah, more you cannot expect. Yeah, and with if there other more involved methods where you actually look at the problem that you want to solve, they can do this much more efficiently. Yeah, so Richard's extrapolation is very fascinating, but never believe that this is the most efficient solution to your problem. It usually is not, but it's the one where you have to use the least thinking, yeah, which is also, which in itself has its advantages, yeah. So this is, so you can, because all you need to do is to solve the original problem several times and then put everything here together and get this result. Okay, by the way, this also does not work for nonlinear problems where you have some chaotic behavior like in turbulence also. It only works for averages, not for real results. Okay, bashing my favorite topic. Now we can use higher order offset functions, yeah? With, we can have here, we specify this by n, any order, and we call this with any n, and we get the weights that we can pre-generate, and then we'll get these functions that we need to solve. So, for example, I mean, this used to be the very simple sine function, yeah. So, if we want to get high order, did I actually call simplify? I don't know whether simplify does anything to this. How long does it actually take to evaluate this? It doesn't take long. Do we want to try to simplify this? Why don't I see anything? Is it still running? Do I get a result? I mean, do I actually get told whether okay, I'm currently not sure that, I'm so used to technical problems that we had here in the past that I just think it doesn't work here. Don't know what's up. Just go to the last slide of today and see how our higher order methods, how they perform. Okay, we have got third order, I believe, and fourth order here. So, oh my God. Kind of darkish orange. Is darkish orange that one? So this apparently is the fourth order stuff. And where do we got? And then this here must be the third order stuff. Okay. Okay, so you see the first order stuff is kind of larger. Maybe you go to the upper ones here. Okay, so this here seems third order, and this here seems first order. And I mean, H we have an implicit, so, it's all solved already, right? So we just, so there is no integration going on. All we need to do is to put H into it and evaluate the function. Yeah? So, and something is wrong here. So this is why we stop now. Right, so I cannot, for whatever reason, I can't evaluate this anymore. Anyway, we'll kind of reach also our time constraint here. Now, there will be no recording of this next week, but we'll have an exercise on the Richardson extrapolation. And I will now, now it arrived and did something, but anyway, I'll stop here. Yeah, thank you for listening.